Good afternoon, everybody. My name is Søren Decker. I am Professor of Liberal Arts and Sciences Education at University College Maastricht. And today I am serving as pro-rector for Pamela Habibic, under whose authority, hopefully, we will be able to confer a doctorate in about an hour's time. I'd like to welcome you all to this defense. I will open it in a second, but I always feel it's important to say that even though this is a formal occasion and we will observe all traditions as we should, this is also a celebration of an awful lot of work that has been done to come to this day and to produce this lovely little booklet. It seems very small and very compact, but I think everybody here knows what an enormous amount of work it is, and that work is what we are celebrating today. So, well, enjoy the show. Hereby, I open this academic ceremony in which Jian Liu will defend the academic thesis entitled Lignin-Based Materials with Intrinsic Recyclability. May I invite you to present a summary of your study and the conclusions of your thesis.
Hello, can you see my screen? Yes, good. Okay. Hello, everyone. My name is Jian Liu, and from Maastricht University. The title of my defense today is Lignin-Based Material with Intrinsic Recyclability. A linear economy is a traditional way of running things based on the idea of take, make, use, dispose. It means we take resources, turn them into products, use them, then throw them away. This approach relies heavily on the resources, especially on the non-renewable ones. The problem is we are using these resources much faster than the nature can replenish them, which could eventually lead to them running out. In this context, building a green economy is absolutely essential. Renewable biomass resources are the key to making sustainable material. And lignin is the most abundant natural aromatic polymer on Earth. It's a non-food biomass resources. By adding lignin to the system, it can increase the thermal stability, mechanical properties, and chemical resistance. So, lignin as a base of the material is a great way to tackle the issue of the renewability. Besides the renewability, sustainability is another challenge in transitioning from a linear economy to a circular economy. In a circular economy, the 3R principles guide us in developing the new material. The 3R principles is the reducing, reusing, and recycling. The 3R principles are pretty easy to apply to the thermoplastic, but it's much harder with the thermal size. That's because the thermal size have the fixed cross-linked point in their structures. This cross-link give the thermal size strong properties, but they also make the thermal size difficult to recycle or reuse. We want to create a material that combines the best of the both thermoplastic and thermal size. It could be strong, like the thermal size during use, but under the certain conditions, it could be recycled or reused, like the thermoplastic, kind of like the glass. It can be reprocessed when needed. Okay, here comes the concept, the covalent adaptable networks. The covalent adaptable network is a new type of the material that connects the thermal size and the thermoplastics, solving the recycling problem of the thermal size. What makes the covalent adaptable network special is they use the dynamic covalent bonds instead of the regular covalent bonds. These dynamic bonds can exchange, which allows material to be recycled or reused. There are two types of the kinds, dissociative kinds and associative kinds. In dissociative decays, the cross-link density of the material changed with the temperature. That means a higher temperature, lower cross-link density. When the cross-link density is low enough, the material can liquefy. A good example is the Diels-Alder reaction. In associative decays, the cross-link density there is a fixed cross-link density. That means new bond form, only one old bond break, and both processes happen at the same time. For example, the transesterification in epoxy system. So here comes the question. In a circular economy, how can the sample size achieve renewability and sustainability? My answer is bio-based material that combined with the covalent adaptable network can achieve both of these goals. Next, I will explain my answer further by going over the properties of the different kinds of material. There are three types of the chemistry I have chosen. They are Villagers uracil chemistry, imine chemistry, and transesterification. We compare the mechanical properties of the different kinds and found the transesterification kinds has the best mechanical properties. This is because the side reaction during the bond exchange, the irreversible bond forms, which further increase the cross-link density of the material, so significantly improving the mechanical performance. The rheology of the material is used to describe the dynamic exchange process at high temperatures. We found the imine kinds have the lowest activation energy and the TV, which is because of the modified lignin with the aldehyde group we made had the lowest modification degree. To improve this, we add some commercial dialdehyde to the system. Even though the dialdehyde content is only 7% of the total network weight, but it still increased amount of dynamic bond in the system. And these bonds are temperature sensitive. As a result, the material show a lower activation energy at TV. On the other hand, the transesterification kinds show the highest activation energy and the TV. This is due to the unique nature of the chemistry. Unlike the transesterification in epoxy system, in our work, we use a ring opening reaction between the anhydride and the fatty alcohol to create networks. At a higher temperature, the ester bonds are catalyzed by the neighborhooding carboxy groups, which allow them to reform into the cyclic anhydride structure. Essentially, this is dissociative decays. And creep is a double-edged sword for the CANS material. On one hand, we want the material to have the dynamic exchange properties, but on the other hand, we also want the material to maintain stable at a higher temperature. So looking at these results, the Villagers uracil kinds and the imine kinds inevitably its appearance permanent deformation when the temperature increased. Well, for the transesterification kinds, because of the irreversible bonds forms, so it shows a stable anti-creep performance. And the reprocessability of the material is our ultimate goal. We found the Villagers uracil kinds, the imine kinds, show really good reprocessability properties, but the recycling performance of the transesterification kinds, it drops significantly after the second circle. This is because of the side reaction. The irreversible bonds lower the recyclability of the material. Okay, Based on the performance about the vlogous urethane cans has a moderate exchange activation energy, the lowest mechanical properties, and the most significant creep at high temperature. So we chose the vlogous urethane cans for further enhancement study. There are many studies has showed a different way to enhance the cans material, like the covalent bonds, the fillers, the metal coordinations. But in our work, we select the hydrogen bond and the crystalline polymer, because both of these systems are temperature sensitive, so they will not affect the recyclability of the material. First, let's talk about the hydrogen bond enhanced system. We prepare the amino-ended non-isocyanase polyurea prepolymer, then cross-linked with the modified lignin to prepare the networks, and the urea bonds in the system can provide rich hydrogen bonding. And this hydrogen bonding help to increase the properties of the material. Okay. The hydrogen bonds can catalyze the bond exchange of the material, resulting the reducing the activation energy. Additionally, the hydrogen bond can significantly improve the anti-creep performance of the material. The second enhancement measures we chose is using the semi-crystalline polymer. PPDL material is a semi-crystalline polymer. We made this polymer from the monomer PDL. We ring opening reaction followed by amine modification, then cross-linked with the modified lignin to prepare the cans material. From the DSA results and the optical microscopy, we can find these beautiful crystals. And these crystals gradually melt as the temperature increase. These crystals significantly improve the mechanical properties of the cans material, with stress at break increasing by 60%, the Young's modules increasing by 80%. In addition to introduce this kinds material, I will talk about some interesting applications. Okay, first, let's return to what we need to do in a circular economy. We need to do reducing, reusing, and recycling. For the reducing means we need to use this material for a longer time. So the repairability is important. We have developed a repairable lignin coating. When this coating got damaged, it can be easily repaired by applying heating. About reusing, we have created on-demand adhesives. These adhesives show strong bonding strengths at room temperature, just like the commercial thermosize adhesives. When the bonding is no longer needed, it can be easily removed with the solvents or the heating, which allow the adhesive layer or the substrates can be reused. The third application is the photothermal conversion material. Lignin as a natural photothermal conversion particles, it can convert the light into heat in just 90 seconds. The surface temperature can reach 146 degrees. This temperature is enough for the material repair or even for the recycling. We combine the photothermal conversion material and the semi-crystalline polymer. Then we created a light response shape memory polymer. Lignin is responsible for the converts light energy into heat, which is used to melt the crystals, and the material can return to its own its original shape. Okay, let's recap our work. We start from the biomass material, the lignin. We have used the dynamic chemical bonds to prepare the recyclable networks, which show great potential for variety applications. So back to the first question. In a circular economy, how can the sample size achieve renewability and sustainability? My answer is lignin-based kinds can achieve both of these goals. Okay. Finally, I would like to thank my supervisors, Professor Katrin Bernas and Professor André Pich. Under their guidance, I have learned how to test a hypothesis with well-designed approach. And with their help, I have published 3 papers and actively promote the potential of the cans at several conferences. At the end, I would like to share my book cover with you guys. This cover, the lignin can be better. The lignin can be better. Oh, thank you, guys.
Thank you, dear candidate. Thank you for your presentation. The opposition will now be opened by Professor Dr. Romano Oro, Professor of Organic Chemistry at Maastricht University.
Okay, thank you, Mr. Chairman, for giving me the floor. And thank you, dear candidate, for the presentation and also for this very beautiful thesis that you have produced. It's really an impressive amount of work. There are really quite a number of interesting chapters, and they all deal with, let's say, recyclability of, let's say, lignin-based type materials. Well, the first chapter that you have is immediately also a chapter that I have some small questions about. So the first questions I would have is they refer to the page number, what is it, 15 and around there. So you list there a whole bunch of, let's say, approaches that one can take to make a covalent adaptable network. Well, among them there are strand esterifications, etc. And I would like to ask you, this is just an informative question for me. So in the middle of this page 15, you see the schematic diagram of a Diels-Alder reaction. Apparently these processes have been used also for the synthesis of can-based materials. So is this restricted to the type of Diels-Alder reaction that you depict here on the scheme, or can this also be hetero Diels-Alder reactions?
The Diels-Alder reaction?
Hetero. So I mean, with a hetero Diels-Alder reaction, a Diels-Alder reaction that has as one of the atoms in the either the diene or the dienophile a hetero atom, can be an oxygen or a nitrogen. Are you aware of literature in that sense?
Oh, sorry.
So this was just an informative question. So it's not a problem if you don't know whether it's there or not. But it would, if you would do a hetero Diels-Alder reaction, then you would form a heterocycle instead of a carbocycle. So a 6-membered ring with at least 1 or maybe 2 nitrogens or oxygens in there. So this Maybe I will come back to that later on because I think this could offer some opportunities, but for the moment I let it to rest. So I will move to another page, and that's also in the introduction, because that's more the end of the introduction where you discuss for a number of monomeric, let's say, aromatic building blocks that you can get from lignin or lignin-based materials. So you describe syringaldehyde, phenolic acid, etc. And then you also describe an example on page 37 where you use eugenol as a where the eugenol was used as a building block for making these cans. So also this is just an informative question. So in this scheme that you show here, there is a reaction from this eugenol with POCl3 to form, let's say, the phosphine intermediate. And then you go on by epoxidizing it and then breaking down again. So in the end, you would have there as a waste material phosphine oxides. Is that true?
Yes.
So in that sense, that would not probably be a very sensible way for making, let's say, a sustainable type of material.
Yes. Is for this study, it's not sustainable, but for the eugenol, because of the functionality, it's not enough. So we need to prepare we just need to increase the functionality of the monomer. So we normally use the POCl3 or use the to just the Williams reactions to connect the two monomers together or more.
So this would probably not be a very sensible building block actually to use, because you would always end up with a very dirty process, or not?
Yeah, I think it's dirty. But here I just want to introduce the possible way because this reaction also from the reference. I just show the different methods to prepare the cans material from the lignin small molecules.
Mm-hmm.
Yeah.
Okay. Well, these are just introduction questions and not on your real work, your own work. So I would like to go to something that you really did yourself in the lab. That's mainly focusing on chapter 3, the lignin-based imine covalent adaptable networks. And let's see, I had a question in the beginning. Yeah, so my first question about these heterodyl-alder reactions. When I was reading this, and this is just asking you of an opinion whether this could be a viable process or not. So you have listed there in scheme 1 on page 97 a number of ways of how imine exchange could be used in a process to make covalent adaptable networks. But in principle, you could also do then with this imine a heterodyl-alder reaction. Do you agree with me or not?
For the imine exchange, normally there are 3 types of the imine exchange: the condition, the immunization, and metastasis. And
okay, let's move on. So I leave the heterodyl-alder to rest. So I would go to another question then. So that is on page 105, where you have, let's say, shown. Oh no, sorry, I'm wrong. It's even one back. It's on 103, where you use terephthaledehyde with this, let's say, lignin-derived diol, and you make the acetal as a sort of intermediate product. That's correct?
Yes.
So one question is, these acetals, they are usually not very stable. So how stable are these acetals as intermediates?
For the modified lignin, we didn't test the properties, but for the material, because we prepare the kinds of material, the acetal bonds and the imine bonds, they are both not stable in the acidic conditions. But we found in just in acidic solution, it's stable. We need to add some solvent, organic solvent, to first swell the material. Then we can use the acidic to degrade the material.
Mm-hmm.
We found, because for the imine bonds, it's reversible, and we try to recycle the material in a solvent way, but we found the mechanical property decreased. Then we got a conclusion, maybe some acetal bonds in the structure degrades. So that's affect the recyclability of the material.
And in these type of, or let's say, structures that you show here, I can imagine that in a lignin-based, let's say, surrounding, also hemiacetals might be relatively stable or not. Like in normal sugar chemistry, they also exist as a hemiacetal, which is actually the only example that I know of in the nature that a hemiacetal is relatively stable. But are these also relatively stable as a hemiacetal?
For the modified lignin, we didn't test
Okay. But, well, okay, let's go on. I have another
one
question.
Short one?
One short one. Yes. Okay. So that's actually on 105, where you make from this acetal with diamine this imine product, and then this imine is then, of course, used in the covalent adaptable network. So again, here you could next to, let's say, forming the imine, also do a heterodyl reaction as a let's say follow-up reaction, but then you would get heterocyclic products out of it. Is this something that could be working or not? So don't focus on the reaction itself, but on the product that could come out. So you would get a heterocycle out of it.
If we got the side reactions, I think it will decrease the recyclability of the material. But we
decrease. You say decrease?
No, the recyclability of it. Yeah.
Well, a heterocycle is usually less stable than yeah.
It's
okay. I think in view of the time, I give the floor back to the pro-rector. So
thank you, Professor.
Thank you. Yeah.
The opposition will now be continued by Professor Dr. Renaud Nicolai, Professor of Macromolecular Engineering from the École supérieure de physique et de chimie industrielle de la ville de Paris.
Thank you, Pro-Rector, Professor Decker. First, I would like to congratulate the candidates, me too, for excellent work, both in terms of experiment conducted, analysis of the result, PhD thesis and presentation. And I would like to discuss more conceptual question, maybe as compared to what was discussed, more general question with regard to your system and covalent adaptable network in general. So my first question would be, what are the properties you were specifically looking for with lignin vitrimers as compared to lignin material which are not vitrimer or canned?
the mechanical properties and the recyclability.
So with regard to mechanical properties, could you elaborate more precisely which property you would be looking to investigate and look for?
For the mechanical properties, maybe just the like the stress at the brake, the Young's modules. Yeah.
And for example, what would be the trend you would expect?
Yeah, from our study, we found the more lignin weight percent, the more brittle, the more the higher modules we will get.
And so here you use the concept of cans to introduce a soft segment in the material. Could this be done using other approaches?
Sorry, could you repeat?
So you mentioned a difference of brittleness based on the content of lignin. So what if we make composite with soft segment, but which are not vitremer? So what will be the advantage of or the interest of making a vitremer or a can? But I will skip this question because I will come back to this. You mentioned recyclability.
Yes.
So you would classify lignin as a thermoset or a thermoplastic?
Lignin. You mean the raw material lignin?
Yes.
It's a thermoplastic because at a high temperature, there is TG about lignin about the lignin in our lab. The TG is around 150. Then
Yes.
about TG, I think it should be viscous states. But for the lignin, it really depends on the molecular weight. Because the molecular weight we use is because the lignin we use is soda lignin, the molecular weight is around 9K. When I do the TGA measurements, you put the lignin powder to the pan. After the measurements, you can still find some powder. So, but for the low molecular weight of the low molecular weight lignin, you can find the viscosity of the lignin. So it's quite hard to describe. It's a small size material or small plastic material.
So another way to say this is that you mentioned it. There are side reactions associated to the process of lignin. When we heat this material, due to its composition and functionality, it leads to side reaction and creation of static permanent crossing. This is correct?
Yes.
So my question is, what did you do to prevent or decrease this by making vitremer? Or
you can both. During my preparing the materials, I didn't do any special ones, but we can prepare the kinds under the nitrogen. So maybe under nitrogen it should be fine. It's better.
But did you make some modification of the function which you suspect to be associated to side reaction during the transformation into vitremer or cans?
For the because when you prepare the cans, it's quite difficult to get the to how to say to describe the side reactions, because it's a cross-linked system. You cannot measure with the MR. You just can find some peaks from the FTIR, and it's not reliable. And how to say, I
So-
mean, if we got some side reaction, it will affect the recyclability of the material. But for my study in the velocity rosin cans and the imine cans, it's good. I didn't find the decrease in the recyclability, but for the transester replication cans, yes.
How would you, so in the field of cans and Vitrumer, let's speak about Vitrumer. How could you, what would be the impact of this side reaction on the reprocessability? What type of property would you look to try to pinpoint that side reaction are taking place?
This side.
So these materials are reprocessable.
Yeah.
So they have the ability to flow. So would this side reaction impact this ability, and how could you show this or investigate this?
Yeah, you can test from the DMA. For example, if you got side reaction, especially for the covalent bond formed, I think the cross-link density should be increased. And you can also get this information from the real meter, from the rheology of the material. If you got side reaction, I think the stress relaxation time it should be increased, and the side reaction will increase the activation energy. It show a higher activation energy. Yeah.
Okay, so I would, yes, I think one way is indeed to look at the viscosity. So you mentioned activation energy. So that's an important parameter for this material which you looked at. And so today and in your manuscript, you mentioned some activation energy. So today it was slide 13. You measured activation energy for vinyl reduced urethane system, for imine-based system, and transesterification-based system. To you, this activation energy, what do they reflect in terms of mechanism at play for so the melt? So this activation energy measure which processes are dictating this activation energies?
From the activation energy,
So, for example, you have
oh, okay, it's fine.
you have some activation energy for vinyl reduced urethane in your system. How do they compare to activation energies that could be measured on small molecule?
Sorry, what do you mean? You mean the activation method?
So I can take two vinyl reduced urethane species or one and an amine, and I can make exchange reaction at different temperature, and I can measure the activation energy for the exchange reaction. I would get a value, and I can do what you did. I can measure the activation energy of the Vitrumer through different processes, and I would give an activation energy. In your case, do you think they compare? And if yes, why? And if not, why?
It's not it's comparable because the lignin weight percent in the system is similar, and for the different, yeah. If we just study the lignin constant in the system, we got the similar lignin content in the system. So I think we can compare the activation energy, but for the different chemistry, for example, especially for the transesterification, we use a dissociative kinase. It's a little bit different. Oh, it's
And so for a simplification, so it's a little
yeah, because
Can
if you want to compare results, it's quite difficult. You need to have the same modification degree. It's quite difficult because for the imine system we got a the lower modification degree. So we add some commercial dialdehyde to a system that increase the dynamic bonds in the system. So if you just compare the activation energy,
So for example, if we go back to vinyl glycerate,
yeah,
if I record it properly, I think the activation energy was 130 kilojoule per mole.
Mhm.
I think this is what you measure. And if I recall properly, I think the activation energy for on small molecule, on model molecule, is more around under the same catalysis, 70 kilojoule per mole. So this is a significant difference. So
yes, yes, it's a difference. We got a higher activation energy. I think because the lignin is with a higher molecular weight, and the lignin can slow down the flow at a high temperature.
okay.
Yeah.
So
Um,
last one, or I can stop. Maybe a last one. Oh. So you mentioned dimensional stability, like creep experiment. So how can you improve dimensional stability in vitrimers? What kind of trick can you think of to try to improve this?
Repeat your question. So how
So
can you increase the
yes,
recyclability?
no, the dimensional stability, the creep resistance of a vitrimer.
Yeah. For the creep, we can increase the TG of the material.
Sorry?
We can increase the TG of the material.
Okay, and this would be my very last comment. So in the process of transforming lignin to vitrimer, what is a change of, is there a change of TG and in which direction?
In the lignin case, the TG, the higher lignin weight percent, the in the system, the higher TG we got.
Okay, I will stop here. Thank you very much. And thank you, Prorector.
Thank you.
Your microphone is not on.
Thank you. The position will now be continued by Dr. Maarten Smulders, Associate Professor of Dynamic Polymers at Wageningen University.
Thank you, Pro-Rector. Dear candidate, first let me also congratulate you with your thesis, which I've read with great interest. It's a topic also close to my heart, the recyclable materials, covalent adaptable networks. I also very much appreciate, as an organic chemist, that you also looked at dynamic chemistries, as you already discussed today. And I hope to have a nice discussion with you about your thesis, the work that's in the thesis. But before going to the content of the thesis, actually, what struck me, receiving a hard copy of your thesis, actually, in the title, I read the word intrinsic recyclability. And actually, that word intrinsic got me thinking, how should I interpret this? I mean, I guess intrinsic, you could say, well, that's something then recyclability happens spontaneously. But I guess you really want to control how, when recycling happens, only after the use of the material. So as a first question, can you maybe elaborate and explain to me how I should see this, this intrinsic property of recyclability in your materials?
The title, intrinsic recyclability. That means we prepare the lignin-based material, combined with the kinds, so the material can recycle.
Yeah, but that I can see that. But in what way did you add the word intrinsic? Like, again, it would suggest to me that it happens spontaneously or without external influence. It's an intrinsic property. So yeah, well, can you think of another word maybe to describe the recycling that you propose? I mean, I can also see from a chemical point of view what's happening, but what would be an alternative way of phrasing this type of recycling?
Because for the cans material, because we want to prepare the cans material from the lignin. For the cans material, it show the intrinsic recyclability because of the dynamic bonds.
Yeah, actually, the words that came to my mind when I thought about this intrinsic. So it's really, that it's really, let's say, with high value recycling. It's chemical recycling in the sense that you don't use, let's say, the chemical bonds inside the material, but you can actually address them. So I know that those were words that came to my mind. So okay, thanks for this first answers. Then I actually had a question about your propositions, and maybe I can read them out loud. This is online defense, so I was told I can't ask your paradigm. So actually, my question refers to, first of all, proposition 3, where you actually state, cans offer a promising approach to designing high-performance, sustainable materials that can be fully recycled through reversible chemical reactions. Very nice, positive statement about cans, but actually, proposition 9, you state, although dynamic bonds can enhance the recyclability of lignin-based materials, the high temperature and pressure involved in the recycling processes may lead to deterioration. So actually, it was a bit of a, disappointment to read. So it somehow seems it's not only, let's say, positive, the research. So how should I combine these two propositions? What's then the solution to that, the deterioration that you propose in proposition 9, right? Is there a bright future for these lignin-based cans?
For the number 3, because that's from the most of the reference of the cans, it show it's a promising approach. But from my study, I did a lot of lignin-based cans. Then I found due to the high temperature or the high pressure, the recycling it's barely for the transaction verification. In my study, it's not good. But in some study, they use the same chemistry, the transaction verification. It show really good results. But it's just for the lignin-based kinds. For my study, sometimes it's just
no. So if I can summarize your statement there, your proposition 9 is more about the use of lignin, and it's although it also has its positive aspects in terms of this material performance, you actually want to express the challenges related to that, its stability. Yeah, so it's not only about covalent adaptable networks. Have I correctly summarized it? Okay, very good. Thanks. Then let's open your thesis. And actually, I would like to start in chapter 2, where you present lignin-based cans based on phenolic urethanes. And actually, my first question is related to the modification of lignin to introduce an acetoacetate group. So actually, it was interesting to read that you also try to quantify this. And for this, actually, you also do some NMR experiments and making use of nitromethane as an internal standard. So like I said, if we go to figure S7, page 79, actually, you've summarized the results there. And maybe what first of all struck me is that the spectra in S7 seem to be not entirely the same as in S2, right? If I, for example, look at your peak A in figure S2, that's quite a sharp peak, also nicely highlighted in a green box. But then if I look at S7, it seems that this sharp peak has all of a sudden has widened. You also see a shoulder, let's say around 2.4 ppm. So can you say something? What's the difference between those two spectra in terms of the conditions under which you measure them, apart from that, at the addition of the internal standard?
oh. the peak of internal standards, it's not in these figures, I'm sorry. It should be in 4.7 ppm. And
I think, I mean, the internal standard is there, right? I mean, in S7. But my
the
question is
internal
more about...
standard not in the figure. Yeah, sorry.
No, it's not in the... My point is more if you look at peak A,
Yeah.
let's say the methyl group on the acetoacetate. In figure S2, it's quite a nice sharp peak. And then if I look at your S7, where you actually want to integrate a peak, it all of a sudden becomes a bit of a broad peak, also shoulders, let's say, on the left side, maybe a little peak on the right side of the so it seems like this nice peak in figure S2 has all of a sudden expanded into a bigger, wider peak with even some shoulder. So what happened here experimentally? How did this change? Do you know?
Oh, I don't know. Figure S2 and the figure S. Which figure?
Yeah, S2 and S7, as far as I can understand, it should be the same spectrum, right? The top one in S2, the red one should correspond to the blue one in S7.
Yeah, with S2 without the internal standard, S7.
Sure, yeah, I appreciate that, but maybe could it be that you use a different concentration in both spectra, and that has a result on the maybe the solubility. I'm not sure how well soluble your polymer is in DMSO.
Yeah, it's in DMSO, and without the internal standard, the concentration is 10 milligram per millimeter or DMSO. But for the internal standard, it's higher. It's around 40 milligram.
Okay, so you went for a higher concentration. Why was that?
Yeah, with the internal standard, the high concentration. Yeah.
Yeah, but why did you do that?
Because
yeah, no, sorry, go ahead.
Because
yeah,
there's a procedure from when we do some quantitative the test like the 31 PMR or some the QMR, which we always select the higher concentration. And
yeah, I can see that. It also seemed in this case to somehow broaden your spectra, which if you also want to do quantitative NMR, and NMR integration might also be disadvantageous, right? If you have less resolved peaks in your spectra. Maybe a final question, of a minor question in between. I also couldn't help noticing those two peaks, let's say just below 3 ppm, which I gather are DMF. So where does this DMF come from? As far as I could tell, you don't really use it in your, I don't know, in your procedure. So is this has this something to do with solubility, or can you account for the presence of DMF in your basically I think in all your NMR data in this chapter?
Oh. No, I didn't use the DMF because for the modification I used the dioxin.
Okay, I thought I wasn't sure what it might have to do with solubility, or maybe you reused the sample that you also did for, I don't know, I'm not sure whether you did. I think in one of your chapters you also mentioned GPC for which you use DMF. So in fact, in several of your spectra there's DMF, but you didn't intentionally add it, I gather from your answer.
Yeah, because for the modification, no DMF inside. It's dioxin.
Okay. I think you already see the prorector. Yeah, I think I'll seeing the prorector already on my screen. I think I'm going to thank the candidate here and hand back to the prorector. Thank you.
Thank you very much. The opposition will be continued by Professor Dr. Martin Honing, Professor of Analytics and System Imaging at Maastricht University.
Thank you, Mr. Prorector. Dear candidate, congratulations with this, let's say, a laborious type of work and a beautiful overview of the possibilities of lignin-based you said maybe thermoplastics, but maybe even advanced thermosets. But that's all about definitions. And I would like to start with some definitions, because you used in your thesis some definitions or claims, and I would just like to get some clarification. And on page number 10, you start your thesis, and you start to say that the heat and pressure patent, which was filed in 1907, is considered the most important one. And that's just an opening sentence. And then as a non-specialist, or at least as a chemist, I would say, there has been a lot of patents, of course, in chemistry. Why is this the most important one? So can you elaborate on that? Or did I misread this sentence?
Yeah, because the small size material was introduced from this patent.
Okay, so this is the most important patent in the production of thermosets.
Yeah.
Yeah, okay, so that would be nice to know then. And you say that it's still active materials slipped into the category of pollutants. But what do you mean slipped into the category of pollutants? What a depressing scene. So I think you want to say we have been using these thermosets for such a long time. They are still there. We consider them as pollutants, and you say actually it is depressing because we did not come up with a solution.
Because for the small size, we cannot recycle this kind of the material after disposal, and it will pollute the environments.
Oh no, yeah, okay, that's what you just said. So the good thing of your research is you would like to find thermoset type of material or recurable material with the properties of thermosets, which can be chemically recycled. Huh? That's, I think, what you want to say. So why did you say it is a depressing scene?
Depressing thing. Small size is a good material, but we want a better material. Yeah, we want to solve the recyclability of the small size. So if the small size can be recycled, that would be fun. That would be
Okay,
yeah,
great,
more
great.
promising. Yeah.
Maybe we go to a next example, because on page 11, then actually you say, okay, the thermosets, we cannot recycle them. And another bad thing of thermosets is that they will lead to toxicology or endocrine disrupting agents, but that's mainly linked to bisphenol A. So bisphenol A, is that a part of the thermoset, or is that an additive to the thermoset?
Bisphenol A always added to the as a hard segment in the small size.
Yeah.
It's a difunctional groups to the crosslink.
Okay, so there's always some free bisphenol A or as a cross-linker in the thermosets present, leading. Now, when you look to bisphenol A, which is actually a dihydroxy aromatic system, and I understand why this is a strange molecule, but if you look to the phenols of lignin, and of course in your on page 29, like the previous referee also asked you, you used very defined monomers from the lignine. But if you have not very pure of compounds of this lignine, you will have also bifunctional hydroxy aromatic system. So why would lignine monomers not be toxic? If you look to the structures, they are lookalikes. you want to claim that thermosets lead to toxicity.
Yeah.
That is absolutely true. But how sure are you that lignine-based cans are not leading to
They got similar structures. Both of these have they got the benzene ring structure, but for the bisphenol A, I think maybe from the preparation of the bisphenol A, it's toxic.
Yeah, but you did not
Because
test it yourself, and you did not find any literature. You did not test the toxicity of the
I
lignin.
didn't test the toxic of the lignin.
Okay. And maybe a next question, and that's at the end on page 39, where you say the aim and the scope of your thesis. I like this approach where you very shortly say, okay, what do I want to change? But you claim there that the fossil-based materials suffer from price fluctuations. Now, let's say if we look to fossil raw materials, they come from different oil spells. So there's a variation in the raw material. And I think for lignine, for sure, it's the same. Both fossil materials and lignine need cracking towards the monomers. So they are completely same processes, very complex, and there will be also price fluctuations for the lignine. So why, or are you arguing there is no price fluctuations when you use the lignine-based cans?
Because we use the lignin, it's a soda lignin, it's a byproduct from.
Jian Liu, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense, and I request that you and your company await the results of our deliberations and our return. Jian Liu, the degree committee here present online has assessed the quality of your thesis and of your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Dr. Bernards is authorized to confer upon you this academic distinction in accordance with Dutch university custom. And I therefore invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I do.
By the authority vested in us by law and in conformity with the decision of the committee, here present online, I hereby confer upon you, Jian Liu, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, you will soon receive the degree certificate signed by the rector, the secretary, and the supervisor affixed with the official seal of the university shown by the beadle.
I believe we have time for some personal words from the supervisor. A laudatio, perhaps?
Dear Jian, congratulations with your PhD. What an achievement. I'm very proud of you. I still remember when you arrived. The initial period was not so easy. Everything in English, and sometimes you maybe even didn't understand us, another culture, another way of working. However, very fast you adapted and you picked up everything. Despite the fact that we had the COVID lockdowns in your first year of PhD, you managed to be productive and organize your work. It was a pleasure to work with you. You were always coming with new ideas and you made sure they were executed at the highest scientific level possible. Even when something failed, you always managed to come with a creative solution. Your work attitude resulted in a high productivity, 3 accepted papers in highly ranked journals, 2 in submission, 1 review ready for submission, and an other article in the pipeline. You always knew to find the right collaborations to speed up your work and complement your expertise to achieve a higher level. You started the project with Enzo to combine the nipus with the lignin cans, resulting in creep-resistant cans. On your initiative, the photothermal conversion strategy was introduced with near-infrared light. You read about this principle in an article, and you immediately saw the potential for your own work. You went to the people from circular engineering to figure out which tools had to be ordered. Unfortunately, the ordered tools from AliExpress did not do the job. But determined as you are, you did not give up. You contacted the professor whose paper inspired you, and you arranged a meeting with him. Very soon, you could send samples, and with the right equipment, they could do the trick. Thanks to the collaboration with Professor Joost Brancard at Brussels University, you managed to study the DMA of your shape memory polymers. I also want to mention your most recent collaboration with Professor Philippe Evon from Toulouse on improving the water resistance of plant-based fiber boards using your lignin-based cans. I hope that your last analytical data allow us to explain the results such that we can make another nice publication together. Finally, thanks a lot for pushing the Lignin project further. You went to several conferences to present your work. Your first conference was Bright Lens Polymer Days in 2021, just in between some COVID waves. Do you remember the Friday before the conference? I called you in my office and I asked you what clothes you were going to wear at the conference. For the audience, you should know that Jian, who is an avid basketball player, was in that time coming to the lab in comfortable sportwear, generally a jogging outfit. You indicated that you wanted to go in your traditional clothing, after which a conference dressing session with the women of our lab followed. During weekend, you bought a costume, and that turned out to be a clever decision, since you had to come to stage at the closing ceremony of the conference as the winner of the Best Poster Award. So you already got external recognition at your first conference, something not many people can emulate. There were also difficult periods. You were normally going to represent our lab with a plenary lecture at the Dutch Polymer Days in April 2023. But unfortunately, you had to cancel. Duty called you back to China because your father was ill. During these months in China, you did not sit idly, but started working on your review. Again, you took the initiative to set up a collaboration, this time even a cross-disciplinary collaboration with someone from economics. This resulted in a unique piece of work that allows to compare the performance of different cans via the ranking system you set up. Let's hope we get through at Progress in Polymer Science. I hope it's clear that I very much appreciated your contribution and I really liked the collaboration. I hope we can continue working together in future and I wish you all the best, both personally and for your academic career back in China. Congratulations.
Thank you, Bernard. Dear Dr. Liu, also on behalf of Maastricht University, I congratulate you with the degree you have acquired and with the wonderful thesis that you have produced. I'm not supposed to leak out of committee, but I can say that everybody was very impressed with the written work that you have created. And as I always like to say, a doctorate is forever. So I hope that you will continue to do such excellent work and take what you've learned here to wherever your travels might take you. I hereby declare this ceremony ended.